This is a video for the pH and amylase required practical from the topic B2. It's looking at the effect of pH on the activity of amylase breaking down starch. So we've got starch, this long chain molecule that's insoluble, so it doesn't dissolve, and we're trying to digest it into sugar, into glucose, using amylase. And we're trying to find out in this practical what is the best pH for amylase to work at, and how does pH affect the activity of the amylase. And you can see there's quite a lot of setup here. So usually what we tend to do is with each of these different pH of amylase, each group does a separate one, and then we pull all of our results together because it's such a long and time-consuming practical. I'm going to start with using pH 4, and I'm going to show you how that works, and then I'm going to go away and collect the results, record them, and we're going to look at how we can calculate rate of enzyme activity. Now, when we first make up, when the technicians make up the amylase, it is at a fixed pH, usually around 5 or 6. And then we use these, and these are called buffer solutions, okay? You have to know about these for the required practical. We buy these and they are specific pHs. So this one is buffer pH 4, this one is 7, and this one is 10. And we can add some of that buffer solution, a small amount, because obviously it will change the concentration of the amylase, but we add that to the amylase to change the pH of it, and then we can put our digital pH meter into the amylase to check the pH of that amylase solution, tweak it around to get it to the pH we're looking for. Now, as soon as that amylase hits the starch, it begins to digest it. So we don't want to have any contamination of using these syringes here to decant the liquid. So I'm going to use a separate syringe for the starch and separate syringes for each of the pHs. I'm just going to grab a beaker quickly to put my mixture in. Okay, so here is my beaker, and my instructions are telling me that I'm going to mix 5 millilitres of starch with 1 of amylase using the syringes, and it's important not to contaminate, I've said that already. And then every 30 seconds, I'll start my timer, and every 30 seconds I'm going to test to see, have we still got starch, has it all been broken down? So I've got some iodine solution here, which is the test for starch, and this kind of orange-brown colour is the negative test for starch. So if there's no starch, it will just remain this colour, and if it goes blue-black, then we have still got starch. So as the starch is broken down by the amylase, you can see this is actually where the beginning was. It starts off very blue-black, and it gradually gets lighter and lighter as there's less starch in that mixture because it's being chopped up into glucose. And then you can see we got to the point here where the iodine hasn't changed colour, so it shows all of the starch has been broken down. So remember, we see amylase as scissors. They're chopping up these long chains of starch into these smaller units of glucose, okay? And that's what's happening in our digestive system to enable those smaller soluble molecules to get through the small intestine and into the blood. That's why we have to digest food. We need to get all of those good nutrients into the bloodstream, and they need to be small to get there. So starch can't get into the bloodstream unless it's broken down by amylase, and then it can be absorbed through the villi of the small intestine and into the blood. So let's take my 5 mils of starch. There you go. Okay, so I've gone to 5 mils, top of the plunger there of the syringe, and that's going in. And then I said I'm going to start with pH 4, and I need 1 mil, which I've got there. Small air bubble in there, I'll do that one again, just to be a true scientist. Okay, there we go. And that's going to go in. As soon as that goes in, I start my timer. Okay. So every 30 seconds, I'm going to decant some of this mixture into my Petri dish and test it to see if that starch has disappeared. Now, I know that pH 4 is not a great pH. It's not very close to the optimum. So it's probably going to take a little while. So I'm not actually even going to bother testing it for 1 minute. I'm going to test it once it gets to a couple of minutes in. Okay, so I'm just going to kind of save my time, save some space on the board here, and test it once it's had a good chance to break that down. We'll come back to that once it's had some time. Okay, we're approaching the 2-minute mark now, so I'm going to give that its first test and pop some into there. And as you can see, I don't want to use too much because I haven't got a lot of mixture in the first place, but you can see there we've got that blue-black colour, so that says that that amylase that's pH 4 has not yet broken down all of the starch that was added to this beaker. So at the moment the amylase is doing its job, it's chopping up that starch, but there's still some starch present, so it's going to take a little bit longer. Now, as we know, enzymes in the stomach work well in acidic conditions. Enzymes in the small intestine work well in alkali conditions. So what we're doing is we're actually looking at amylase, which, if you remember, works in the mouth. It comes from the salivary gland as well as other places. And we talked about that chewing of the bread and the starch being broken into glucose and then being able to taste that. And what we're looking at is what pH would be the best pH to have in the mouth for amylase from the saliva to be really, really effective at breaking down starch into sugar. Okay, so I've now got to coming up to 3.5 minutes. Okay, I know it says there to test every 30 seconds, but experience has told me I don't need to keep testing it every 30 seconds in the beginning stages because it hasn't had enough time for the starch to break down. So I'll just take a bit and do a test. And you might not be able to see it there, but it's definitely edging more towards the brown side than it is the blue-black. So it is starting to break down. It's obviously just going to take some time. I'm going to repeat this whole experiment now for all of these pHs and get some results, and I'm going to add them to my table here, and you can add that then to your required practical placemat sheet. Okay. As you can see, I've now done some multitasking, so I've actually set up all of the different pH of amylase with the starch exactly the same way as you saw before, and I've got a separate stopwatch for each, and I'm going to just systematically keep testing them. So it's about time to do it now. So that's the pH 4, definitely more on the brown side, so that starch is definitely being broken down. pH 5, not there yet. pH 6, looking surprisingly good actually, quite brown. Still not anywhere near being done yet, but we'll keep going. pH 7, okay, that's also breaking down the starch, and pH 8, which isn't looking too good at all. Okay. Okay, so we're now up to about 18 minutes on the first test. So let's test that one now. As you can imagine, doing this in class can get a little bit tedious because you're just waiting. And you can see, hopefully, that is definitely lighter. So it is definitely digesting that starch, but it does take time. So I've prepared lots and lots of spotting tiles now to allow me to test many, many times. Okay, so I'm just going to keep plodding away with this, and I'll recap when we get to the end. So the experiment's now over. I've collected all my results, and you can see now in those spotting tiles the kind of graduation as we go from the blue-black of having lots of starch fading away into the kind of brown colour, and then into the orange of the iodine solution where there was no starch because it had all been broken down, chopped away by the amylase, and it was about looking at how long it takes that process at different pHs to work out the optimum pH. Here are the results we've got, and we can see that the optimum with the shortest amount of time to digest all the starch was 23 minutes, which was pH 6. We've got the worst pH there was 8, so we've probably got beyond 8 and above. A more alkali solution of amylase would probably just denature due to that high pH. We'll have a look at calculating the rate of reaction, and then you can do some graphs in class. Calculating rate of reaction is different in biology than it is in chemistry. Gets the same pattern of results in the graph. Chemistry, we tend to say 1 over time, and in biology we say 1,000 over time. It gives us a bit kind of nicer numbers to work with. So let's have a look. 1,000 divided by 32 gives us 31.25. 1,000 divided by 25 gives us 40, and I'll go to 2 decimal places again. 1,000 divided by 23 is 43.48. I'll probably end up using just whole numbers on the graph to be perfectly honest, but that's fine. 1,000 divided by 42 is 23.81, and 1,000 divided by 47 is 21.28. Okay, so there are the rate of activity. So a short time gives us a fast rate of reaction, a bigger number in rate of reaction. And I'll show you just briefly why this is important in case you're choosing to use this video as a revision tool at home rather than just in class for the required practical. We've got 2 kinds of graph we can draw here. We can draw, and we may see in an exam style question, time and pH. So that we've got slightly skewed results here. It's saying that pH 7 is more effective than pH 6 as in our results, but that always happens. We always get some variation in our results. Let's just concentrate on these for the moment. So we've got a short time there showing us a fast rate of reaction. Now how I've created this graph here is I've actually just taken this graph and flipped it like this to show that a short time is a fast rate of reaction. If I wanted to do this as a proper rate of reaction graph, which is what you're about to do, I would do the 1,000 divided by time to get this data, and then I can plot pH on the bottom of the graph there and rate of enzyme activity up the side here. And our graph should give us some kind of curve like this. Okay, so that's the end of the required practical, probably the trickiest required practical of them all. There's also another video coming looking at doing the practical on the modelling software and looking at interval and how we can change interval, and I'll just talk about that briefly. So we've got pH 6 and pH 7. We know that 7 is somewhere as the optimum. What we can do then using we could do it in real life obviously, but using the modelling program we can easily then have a look at 6.8, 7.2, and look at some of the kind of reducing the interval size. The interval at the moment is going up in 1s. We're going to now reduce it going up in 0.2, but only around the optimum. There's no point trying 4.8 because we know it's not very effective pH for amylase to work. So we're going to focus around this area and reduce that interval down to get a more precise pH. Hope you found that useful. Thank you.